So this section now is not specifically about axiomatic design. So here we're going to be talking about manufacturing, but in the context of axiomatic design. First, this is about manufacturing processes rather than about manufacturing systems. So let's take a look at this. And there's a kind of continuum. It's sometimes difficult to say, this is a process and it's very specific, and this is a system and they're completely different. A system, technically, is anything with more than one component. It could be a system. And so therefore it's very difficult to find something that's not a system. It may be easier to find things that are not manufacturing processes. So if we take a look at something like chip formation, which is represented here on the left side of the screen diagrammatically, this is clearly a manufacturing process. We're removing material, we're cutting metal or something. And then if we look at on the right side, this is more clearly a system because we're looking at supply chain management. And so then in between we've got sort of machine tools and larger processes. And so, all right, let's take a look here too. The process is very clearly where the tool meets the workpiece. So these are clearly manufacturing processes. But sometimes it's difficult to say they're not systems. So the closer to the workpiece modification and the fewer components that are involved, the more it looks like a process and the less it looks like a system. Now, systems are often organizing processes into some sort of system. And you have to be careful because one of the assignments is going to be to find papers on manufacturing processes. Papers that have process in the title are not necessarily about processes because they may be about integrating processes into a system and not actually looking at the process itself. Let's think about energy for a moment. So in manufacturing processes, generally what we're doing is we're applying energy to modify a workpiece to add value to it. And so we're doing some sort of value-adding work. And in fact, some of the very definitions of energy come from machining originally and boring out cannons. Count Rumford was able to show that mechanical work from machining actually could boil water. Now, historically, people have relied on people to supply the energy that modifies the workpiece. Then Count Rumford used horses to provide the energy for boring out the cannons until it was boiling water. You could use water power, so setting up some kind of water wheels. Wind, solar power, stored chemical, so like petroleum products or coal, nuclear. So these are the sources for the energy. Now the importance of the energy in being able to make the energy do work for us really accounts for all kinds of comforts that we have. So the fact that beyond manufacturing, transportation, air conditioning, heating, hot water, all kinds of entertainment come to us because we're able to convert energy from one form to another and put it to work for us. But this is key in manufacturing, and one of the reasons we can have so many remarkable products is that we're able to harness different forms of energy and put them to work modifying those. We all live better now than kings and queens did 200 years ago, before we were able to get so good at converting energy. Just as Nam Tzu asked, is design an art or a science, we might ask if manufacturing engineering, whether it's processes or systems, is an art or a science. And I addressed this in a I addressed this in a paper I gave at the SERP Design Conference at KAIST And it was not actually in 3011, it was in 2011. It's not that futuristic. KAIST is the Korean Advanced Institute for Science and Technology. And I may have misspelled that as well. But, all right, so the KAIST hosted this SERP design conference, and I presented this paper. And so here with some modifications is what I presented a few years ago in Korea. So the objective here was to see if we could develop a manufacturing process design as a scientific discipline, and do this perhaps through the application of axiomatic design. Now, as we've discussed in regard to design, scientific disciplines have a few set of simple laws which can be used to solve a wide variety of problems in that discipline. Manufacturing seems to lack this set of laws that would make it a true scientific discipline. So one of our challenges might be to see, well, what would make sense for laws here? So manufacturing design, if it could be a scientific discipline, would be much easier to understand, teach, and learn. And it would be much easier to apply to solving a wide variety of manufacturing problems than it would be if it's just an experiential discipline. And if we take a look sort of the state of the art, very good manufacturing textbooks, often they're quite thick, a bit expensive, and they contain essentially sequential descriptions of individual manufacturing processes. Usually there's some sort of taxonomy that's used, like here's material removal, of course now additive is going to be becoming more and more popular, then there's forming, and so the problem though is that even with these taxonomies, manufacturing textbooks historically have looked more like encyclopedias. Very often very useful compilations of manufacturing knowledge, but that are essentially best practices, standards, and they don't have any identification of what's common to all manufacturing. What are the commonalities? Just like Newton sees commonalities in gravitation near the Earth and out stretching into the solar system. Are there commonalities in manufacturing that would take us from making software to making cars? Well, we can take a look at some, and in Nam's book, Advances and Applications of Axiomatic Design. FR0, he has a general approach to flexible manufacturing systems. And so maximize return on investment. So then he has two DP candidates depending upon what the situation is. Minimum cost, essentially unlimited demand. And then meet the customer needs where there's a production overcapacity. So when we have overcapacity, we need to be more careful about what we make and how to get customers. Now, generalized decompositions could be useful for advancing design solutions. What would the upper level FR0 be? Perhaps we want to maximize the probability of success in manufacturing. So this might be appropriate for any level of manufacturing design problem and transcends the system and the process design. Of course, we want to be successful. So detailed manufacturing processes, process design to abstractions of manufacturing systems, this would work. Lean should be one system for maximizing success. But this still leaves us a little short because it seems a it's not clear how to apply this. So what we would need to do would be to decompose it somehow. So how would we do this? Well, we want to identify commonalities and generalize. So manufacturing, in general, we can define as transforming resources to meet human needs. So human needs here equate to value. It also needs to provide a return on investment so that it's economically sustainable. So commonality should relate value and return. Now, as we think about manufacturing too, we can think about this in the context of mechanical engineering, so let me go off on a small tangent for a moment. If we look at the development of mechanical engineering, and we take a look at the development of manufacturing, mechanical engineering traditionally was manufacturing engineering. So we're looking at building machines, hence the German term for mechanical engineering, Maschinenbauer, machine builder. So here's an example of a machine from the Industrial Revolution in southern New England. Henry Ford's first car, 1896. It's mechanical engineering. First powered flight. Then we have the principles of scientific management, and this launches industrial engineering, and Taylor, and he's working very much on machining. And then aerospace, first liquid rockets. Now actually Goddard was not a mechanical engineer. But as we look at all of the things that has spawned, this is different applications generally of mechanical engineering. Then, of course, we have World War II and the Cold War, where there's an increase in aviation and aerospace. And then mechanical engineering starts to move away from manufacturing to the research support, the support there is for the development of aviation and aerospace. In 1990, though, the United States has lost much of its advantage in manufacturing, and a group out of MIT starts looking to see what has happened to the American car industry and why is it not as competitive as it used to be? Why does it not dominate North America as it used to? And so then they come up with lean manufacturing. Now, if we take a look sort of at what the interesting problems are, most of these relate to mechanical engineering, and many of them come back to Newton's laws. What we're doing in manufacturing is trying to apply force or concentrate energy in the modification of a product. But there's so when we look at the kinds of problems we see in textbooks, it's very much related to sort of force, deformation, and geometry, and there's no discussion of the larger problems. All right, so let's get back to the larger problems. FR0, maximize the probability of success in manufacturing. So we might say, let's maximize the value added to the product, or minimize the cost. So what we want to do is make the best, most valuable product we can at the least cost or the least waste. One of the important things is that we don't want to compromise value for the cost. If we can't increase the value, there's nothing there. So cutting the cost, if we can't maintain the value, then, or at least adequate value, makes no sense. Now, Professor Thompson, in her 2013 ICAD paper, calls the design intents, say, that begin with maximize or minimize, actually non-FRs, and rather they're selection criteria. So then she takes issue, actually, in her paper with my contention that these upper-level FRs could be maximized and minimized. So let's see how we might state these alternatively now, so addressing the concerns that Professor Thompson has raised. So perhaps it's just provide the required value. So if we know what the customer is looking for, maybe it's not maximizing the value, but let's meet the value that the customer needs, the customer is willing to pay for, that makes sense in this market. And so that's how we're going to provide the success. And if we can control the cost as opposed to minimize the cost. Now, obviously we can't eliminate cost, it's going to cost something. And we want to be aware of the waste, and this can be important. So, we can't make ordinary mechanical devices that violate Newton's laws. We can, however, make designs that violate Sue's axioms. Arguably, they're not good designs. And we can make manufacturing systems that would violate these, say, manufacturing axioms, if that's what we want to call them. And let's take a look at this. Let's take a look at machining. So here we have a depiction of milling, a milling cutter. And here's a classic kind of depiction of chip formation, which is what's going on where the tool meets the workpiece. Now we'll take a look at this in detail later in this class, or in this course. But as we will see, most of the energy in machining is going into the chip. We're doing most of the work on the chip, and the chip we throw away. So is this a good process? It doesn't seem like it, since the value is in the surface that's being produced, and the roughness of the surface and the shape. But most of the energy is going into producing the chip. So one of the things we'd like to do as well is to reduce transportation, since that's just a waste. So we want to manufacture closer to the source of consumption. What about sustainability and cost? Waste is probably not sustainable, although we have a great capacity for absorbing waste. In many places we've run out of that capacity. So waste really should be driving cost. It's at least a societal cost, even if it's not recognized as a cost to the producer of the waste. On a broader scale, if we're wasting energy, for example, wasting materials, there's a limit to what we can do, and we may be seeing the impact of this in global warming. So here's something to consider in looking at waste. And the first canon of engineering ethics is hold paramount the safety, health, and welfare of the public. So there is a true cost to global warming, and it is going to impact the safety, health, and welfare of the public. So we need to be addressing wastes and recognizing that even if there is not an immediate cost to the company, we do have a moral and ethical obligation as engineers to address this. Well, when I was introducing axiomatic design to a company that I worked for in Europe, when I worked for Atlas Copco, somebody said, it's just common sense. Well, so we have common sense, and we can make a little matrix. So there's sense and common. So if there's common sense, perhaps there's uncommon sense. And if there's sense, perhaps there's nonsense. So then we might have common nonsense and uncommon nonsense. So what have we developed here? Are these axioms or rules for manufacturing that address adding value and reducing cost and waste? Just common sense? Or maybe it's nonsense or uncommon nonsense. When we get back to looking at the processes in detail, we'll consider this in more depth. And that concludes the section on manufacturing processes.